Welcome to this webisode for separation processes. In this webisode we're going to look at how to evaluate this integral, which we often use to calculate the number of transfer units in the calculation of a height of a packed bed adsorber. One way to do that is to construct a table of values of 1 over 1 y minus y star for various values of y, graph that against y, and then integrate graphically by either counting the squares or some other numerical technique between y1 and y2, the two ends of the operating line. So I'm going to step through how we would do that. So the first step is to determine values of y and y star at various points along the operating line. So I've done that here in a few different places. So y, to remind you, is the concentration, the bulk of the gas phase at a particular point in the equipment, and at that same point the concentration in the bulk of the liquid phase is given by x, and using our equilibrium curve we can read off the corresponding value in gas phase units. So it's a measure of the composition in the liquid phase at that point in consistent gas phase units. We denote that by y star. So once we've done that for a bunch of different pairs, we can populate a table like this. Now, using our spreadsheet functions, we can just calculate 1 over y minus y star and fill in this value of the table, and then we can start to do our integration. So it's not actually necessary to draw this graph to be able to do this integration, but I've just drawn it here to illustrate it for you. This is a graph of 1 over y minus y star, so this column here as a function of y. These are the values of y. And what we want to do is calculate the area under this curve from this point here up to this point here. So the way that we do that is we construct a bunch of rectangles or trapezoids between different points. So this one here I'll use to illustrate this particular value here. So this value here is the product of 1 over y minus y star multiplied by dy. So we don't use one particular value of 1 over y minus y star, we use the average of two different values. So this block has taken the average value between these two different values, which is the average of these two numbers here, and the width of that rectangle is the difference between two values of y. In this case it's these two values here. So the way that we calculated that number is the average of these two numbers multiplied by the difference between these two numbers. And we just go down this column here, calculating the area of those rectangles, which approximates the area under this curve. And when we sum those up, we get our numerical approximation to the area under the curve. We need to note that since Y1 is actually the composition of the gas entering our system, this is a gas absorption system, so Y1 is the higher concentration in the gas phase. It's higher than Y2. What that means is that in this particular example, we haven't evaluated this integral, but we've evaluated this equivalent integral. So instead of evaluating negative 1 over y minus y star between y1 and y2, where y1 is actually the larger, we've made the larger bound at the top and the smaller bound at the bottom and evaluated it for a positive value here. And that integral evaluates to 3.02, which in this case is the number of overall gas phase transfer units required for that separation.